Hello my dear student, welcome to this new video. First of all, I would like to say wish you a very happy Diwali 2020, since this video I am releasing on the Diwali occasion. Okay, so wish you a very happy Diwali. Now let's start with a video. In this video, the topic that we are going to discuss, this topic is oscillation. From the oscillation, I will discuss the very important points which are important for entrance exams like NEET or JEE Mains. So we'll discuss the entrance level oscillation. Okay, so without wasting time, let's get started. Okay, so in oscillation, let's start with the first point. The first point is difference between the oscillation and SHM. What's the exact difference between oscillation and SHM? That we will see. Now see, these words oscillation and SHM, they are very closely related to each other. Sometimes a student don't even know that what is the exact difference between them. So let's discuss that. Now what is oscillation? Suppose you are having a particular quantity, let's say any particular quantity we are having, maybe velocity or acceleration or displacement, anything. Suppose we are having a particular quantity x. Okay, this quantity x which is there, it is suppose it is continuously changing between two values x1 and x2. That means this quantity is changing from x1 to x2 and then back from x2 to x1. It is continuously changing between x1 and x2. So these x1 and x2 are known as extreme values, and between these two values the x quantity is continuously oscillating. This is called oscillation. Okay, now, oscillation is a periodic motion. It's periodic motion, that is the oscillation repeat itself after regular intervals of time. So this, as I told you, the x is changing from x1 to x2 and then back x2 to x1. This process will keep on repeating itself after regular intervals of time. So it's a periodic motion. Okay, here x1 and x2 that I am talking, the x1 and x2 can be any values. It can be, there's no condition on them. They can have any values. Okay, that means x1 can be 0, it can be negative as well. Sometimes x2 may be 0, it can be negative or positive, anything. So there's no restriction on the values of x1 and x2. So it is called oscillation. Okay, so this is oscillation. It's a periodic motion, that is it repeats itself after regular time. Now what is SHM? Let's see. Actually SHM is a special case of oscillation. SHM is a special type of oscillation only. In SHM what happens, see to it. In the SHM, if we are having a quantity y, suppose y is a quantity, if the quantity y is changing between two values such that the one value is minus y0 and other value is equally positive, that is plus y0. If the y quantity is, let's say, changing from minus y0 to the equally positive quantity plus y0, one is negative and other extreme is positive. One has to be negative, other has to be equally positive. Okay, if the y is changing between these two values, then we can say y is performing SHM. For SHM, one simple rule is there. One extreme should be negative, other extreme should be equally positive. Okay, so this is called SHM. Okay, so there's a minor difference between them. Every SHM, we can say like this, every SHM is an oscillation, but every oscillation need not to be SHM. Okay, like that. So SHM is a subset of oscillation, we can say. SHM is also a periodic motion. Okay, so now this values I told you. So suppose you can take some multiple other example also tell you. If suppose y is changing from -1 to +1, we can say it is a SHM. It is also oscillation, but it is SHM as well. If y is changing from -a to +a, it's SHM. But if y is changing from 0 to a, if it is changing, so negative value is not involved, 0 to a it is changing, so it will be oscillation but not SHM. Okay, clear with the difference? Now how to identify SHM or oscillation mathematically, that I will tell you. Mathematically, what steps you have to remember, that I will tell you. If suppose you are having any quantity, let's say y or something, if any quantity y is there, if it is expressed like this, a sine of omega t, or it can be expressed like this, b cos of omega t. Either sine should be there or cos should be there. Or suppose y is expressed as a combination of sine and cos. That means a sine plus b cosine. It's a combination of sine and cos. So whenever this kind of a y is given to you in terms of sine or cosine, then definitely it is Shm. Remember this, huh? Definitely it is Shm. Because here you can see sine and cosines are there. You know that sine can change from +1 to -1. When sine will be -1, the y will be equal to -a, isn't it? And when sine will be +1, the y will be +a. Okay. So this way it is here. So remember that if sine, cosine or combination of sine cos is there, it is indeed Shm. Okay. But if suppose it is given this way, y equals to a sine square omega t is given, let's suppose. Here square is there. Now everybody knows that square cannot be negative. Square cannot be negative. So this term is cannot be negative. Here y will change from 0 to +a only. Okay. Because square cannot be negative at all. So y will change from 0 to +a. So it is an oscillation, we can say, but it is not at all Shm. It is indeed oscillation, but it is not at all Shm. Similarly, if it is cos square over here, then also it is oscillation. Okay, but not Shm. Clear? Now, sometime what happens? This y equal to a sine square omega t, which I told you, it's an oscillation. So sometime they can ask you the period of this oscillation. That what is the period of this oscillation? So if you need to find period, let's see what you have to do. Here, it's sine square term is there, right? Sine square omega t, you can write it like this: 1 minus cos 2 omega t divided by 2. From the trigonometry, you can understand this. Now, if you just solve it a little bit more, it will be a by 2 minus a by 2 cos of 2 omega t. Isn't it? Now, here if you look at it, this a by 2 is a constant term. That means a by 2 is not oscillating between two values. It is constant. This a by 2 is also constant. Only term which will oscillate, which will change between -1 to +1 or something, that term is this one. This term is continuously oscillating. This is the oscillating term. So if you want to find out the frequency of this oscillation or a period of this oscillation, first of all you have to find out the period of this term. Period of cos 2 omega t we have to find. Here can you see 2 omega is there, right? It's not omega, it's 2 omega here. So what you can do, this 2 omega which you got, you can say it's a effective omega of this oscillation. The effective omega will be 2 omega. Now effective omega you write down this way: 2 pi by t effective. That is the time period. So 2 gets cancelled from both sides. The effective time period of this oscillation will be pi by omega. See this way you can get a period of oscillation. This is a period of the oscillatory motion which is represented by this thing. As I told you, this is an oscillation but not Shm. The period of this oscillation is this one, pi upon omega. Okay. So clear? Okay. One last thing I will tell you over here. See, if the y is given like this, a tan of omega t, okay, tan or maybe cot or something, or y is given by suppose a sec omega t, or y is given by a cosec of omega t, something like this if it is given. Okay, then these are not at all oscillations and not even Shms. They are not Shms and not even they are oscillations, because you might be knowing that sec and cosec, they can go up to infinity also. Sec and cosec, they can reach to infinity also. So if anything, and even 10 can reach to infinity. Value of 10 can be infinite. So these are not at all oscillations. Okay, not even Shm, not even oscillation. Okay, so keep these things at least in your mind. Okay, now we'll move to the next point. Okay, so now we'll discuss the second point in the oscillation. Second point is graphs. So we'll see some various graphs in the oscillation. Okay, the first graph that you have to understand, it is force versus displacement x. F versus x graph. Here x is a displacement from the mean position. X I will plot here and F will be on the y-axis. Now you might be knowing from the oscillation that F in the oscillation, it is directly proportional to -x. Negative sign indicate that F and x both are always in the opposite direction. Here on removing this proportionality sign, we have to put the constant kx. Okay, so if you compare this equation with this one, y equal to mx, so they are very much comparable. Okay, so graph of f versus x has to be a straight line passing through origin, because the equation is similar to y equal to mx, right? So this is a graph of f versus x, right? Now if you see, this graph is not passing through the first quadrant, it's passing through second and the fourth quadrant. Why? Because whenever x is in the positive side, the f is on the negative side, like this. So that's why, since f and x both are on opposite side, that's why this negative sign is there, isn't it? So due to this negative sign, this graph passes through second and fourth quadrant. Now if you compare these two equations, you can understand that a slope, m is a slope, it is equal to k. Yes, slope of this graph, if you find, slope will be equal to k. K is known as force constant, right? In this oscillation, k is called force constant. The slope will give you k. Okay, so this graph we explained. Now suppose one more graph we will discuss. Suppose if I plot the graph of acceleration versus x. Acceleration versus x graph we plot. Okay, so on the y-axis we will plot here acceleration, a. On the x-axis it will be x only, same will come. So you might be knowing that acceleration is given by minus omega square x. This is a formula for acceleration. Here negative sign indicate that a and x both are in opposite direction. That is the meaning of negative sign, isn't it? So a and x both are opposite in direction. This formula is also comparable with y equal to mx. So graph remains same only. You can say similar graph will come for a versus x also. The only difference is, if you are having a versus x graph, in that graph slope will be equal to omega square, minus omega square we can say. And here also slope will be equal to minus k. Okay, so slope will come negative of omega square. Okay, so graph remains same only. So this graph that you can see, it is for f versus x, it is also for a versus x. Clear? Okay, now we'll go with a second graph. Okay, so let's discuss the second graph now. Second graph is velocity versus displacement. Okay, here velocity I have plotted on the y-axis suppose, and displacement on the x-axis. Now if you plot the graph of velocity versus displacement in Shm, graph comes to be an elliptical in shape. It's an elliptical graph. Okay, see, I have drawn a roughly diagram. You can draw a proper ellipse. It will be elliptical. Okay, now how can we prove that it is elliptical? That also I'll show you. Look here. You know that in oscillation, velocity is given by this formula, v equal to omega root of a square minus x square. This formula everybody knows. If you square this formula and just solve it little bit, you will get this expression, right? Now if you solve it little bit more, you will get this expression. Okay, one last step on passing this right hand side towards the left. Pass the RHS on the left side, you will get this one. Okay, just understand this step. So this is the equation that we are getting. It's nothing but a relation between v and x, right? Okay, this relation is very similar to this relation, x square by a square plus y square by b square is equal to 1. See, both these expressions are comparable. So everybody knows that this is the equation of ellipse, right? So that's why the graph of v versus x should also be ellipse. Clear? Okay, here you can see that this is a, you can say this is a maximum value of x. It is equal to amplitude, this one. And the maximum value of velocity will be this much, omega into a. Okay. So this one, it's a maximum value of velocity, it is omega into a. Okay, so it has to be ellipse. Suppose in this equation omega is given 1. For this oscillation omega is 1. If omega is 1, that you can understand that semi-major axis and semi-minor axis will become equal if omega is 1. So when omega is 1, this will turn out to be a circle. This ellipse will become a circle. Okay, so omega 1, that means it will become a circle. So this is a graph of v versus x. Okay, ellipse, you can remember that it is an ellipse, but in the ellipse you can see one simple thing, that if you look at this point, it's a point on the ellipse. At this point velocity is maximum, but displacement is 0, right? And if you look at this point, at this point displacement becomes maximum but velocity becomes 0. Okay, so this kind of a graph you are getting. Okay, keep it in mind. Okay, now this was velocity versus displacement graph. Now one more graph we will go. It is displacement versus time graph, x versus t. Now you know that displacement x is given by this formula, a sine omega t, plus it can be alpha or some phase constant you can give, phi I suppose. Phi is a phase constant. It is also sometimes known as epoch in the oscillation. It's a phase constant. Now since x and time, we have to plot the graph of x versus t, isn't it? Okay. So if you look at it here, sine is there. X and time are connected by the sine term. So graph will be of sine curve. It will be. If I plot here x, here time, it will be a sinusoidal shape. If this epoch is 0, this phase constant is suppose 0. If this is 0, it's simply sine omega t. Here, the graph will start this way and go like this. This kind of a graph will come when the alpha angle or this phi angle that you are talking, phi angle is 0. Okay. Now phi angle can be 90 also. Suppose the phi angle is 90 degree. So this sine omega t plus 90 we will get. So it becomes cos. X equal to a cos omega t will come. And you know that cos graph starts from the top and then it will follow this way. So this will be the graph if the phi angle is 90 degree. Okay. But the phi angle can be between 0 and 90 also. Phi can be between 0 and 90 also. If the phi angle is not 0, not 90, between 0 and 90, in that case, the graph of this x versus t will not start from 0 or maximum. The graph will start from somewhere in between like this. And then this kind of a shape it will take. The graph will start from somewhere middle. Okay, if the angle is not 0 and not even 90 degree. Okay, that you can understand. So this is a graph of x versus t. Okay, so here we discussed all the required graphs from SHM. Okay, let's move to the next point. Okay, so now next point we'll discuss phase difference between x, v and a. Okay, see, x is a displacement and suppose displacement is given by this formula, a sine omega t. Here I'm phi angle I'm not including, but we can include that also, no problem. So this is the thing. Here omega t which is written over here, this is called as phase, isn't it? Phase is basically an angle. This angle helps you in deciding that what is the state of oscillation, that in which where is the body during oscillation. This phase is called. So this is omega t is a phase. Now if you take a derivative of this x, you will get a velocity, right? Velocity is dx by dt. So once you take a derivative, it becomes a omega cos omega t, isn't it? So velocity is given by a omega cos omega t. So it's a omega cos omega t, we can write this way, sine of omega t plus pi by 2. So see, the x is in the terms of sine. So velocity also we bring in terms of sine only. Here if you see, this is called phase of this velocity. So clearly you can see that velocity phase is ahead by 90 degree compared to the displacement. Here you can see clearly that velocity phase is ahead by 90 degree compared to the phase of displacement. Okay. Now again if you take a derivative of velocity, you will get an acceleration, isn't it? Acceleration is given by dv upon dt. So if you take one more time derivative, please take a derivative of this step. Derivative of this one we will take. So derivative of cos will become minus sine. Na? So it comes minus a omega square sine. It's a derivative of velocity. Yeah? It will be acceleration. Now here if you see minus sine omega t term is there. Okay. So if it is a term which is having minus sine omega t, so minus sine omega t can be written this way, sine omega t plus 180. That is pi. Okay. So this equation can be written this way. This is again a phase of oscillation, right? It's a phase of acceleration. So compare these three phases. You can clearly see that acceleration is ahead of the phase by 180 degree compared to displacement. Okay. So acceleration is a leading in the phase, then it is velocity, and the one who is lagging in the phase, it is displacement, right? You can remember this way. X, then V is there. V is ahead by pi by 2, and from V acceleration is again ahead by pi by 2. So overall acceleration is ahead of this x by pi angle. Okay, like this. Okay, clear? This kind of a thing is there. Okay. So remember that it's acceleration who leads, okay, by 180 degree compared to displacement, and velocity is ahead of the displacement by 90 degree. Okay, so here in this diagram you can see the phase difference between any two quantities. Okay, so I hope this argument is very clear, right? Okay, let's move to the next point. Okay, so let's start with the next point. It's a time interval between two positions in SHM. Sometimes the question comes on the topic that you have to find out the time taken by the body to move between 2 points, that how much time it takes to go from one point to another point in the path of SHM. So that I am discussing. See here, this is a path of SHM. X equal to 0, this represents mean position, isn't it? And these are the two extreme position. Now suppose if the body starts from mean position, okay, and it start doing the oscillation. The period of this oscillation is, let's say, t. Look here. T is a period of this oscillation. Okay, then to go from mean position to this extreme position, this time that it takes to go from mean to extreme, this time is t upon 4. You might be knowing this already, right? Okay, now today we will try to calculate that how much time it takes to go from x equal to 0 to x equal to a by 2. Okay, this time we want to find out time taken to go from here to here. Now you may be thinking that if the total time is t upon 4, so the time taken to cover this half distance from x equal to 0 to x equal to a by 2, this time you might be thinking that it is half of t by 4, that is t by 8, but it is not so. The time taken to go from x equal to 0 to x equal to a by 2, this time is t by 6. It's not t by 8 as we expected, it's t by 6. Okay, and the time taken to go from x equal to a by 2 to x equal to a, this time to go from here to here, it is double of t by 6. It's 2 times, sorry, it is 2 times t by 12, and this is also, wait a minute, it is also t by 12. Okay, make a correction, it's t by 12 and then it takes 2 times t by 12. So this will become t by 6 actually, this one. Okay, sorry, I made a mistake. You make a correction over here. This is t by 12 and this time is t by twice of t by 12. Okay, it's simple concept, you can understand this. Okay, now here it is there, so keep it in mind. If you add this t by 12 and also 2t by 12, if you add these two, you can get t by 4 very easily. Okay, getting this? But now some student might be having a doubt that how to prove that it is t by 12. How can we prove that time taken to go from x equal to 0 to x equal to a by 2 is t by 12? So if you are having a doubt that how to prove this point or how to find this time, so that I am clearing now. Okay, see, let's see the proof of this point, that how it is t by 12. Okay, see, when the body is at x equal to 0, okay, from x equal to 0 the body is going to this place, x equal to a by 2, and we have to find out this time, right? We have to prove that it is t upon 12. So what to do? It's a very simple thing. Suppose when the body is at x equal to 0, from there time is starting, here t equal to 0. Okay. As soon as the body will leave from mean position, the time counting will start. That means the time started from the mean position. Okay, in this case, at t equals to 0, the body is at x equal to 0. So in this case, epoch is considered as 0. Epoch will be 0. Now, when the body reaches here at x equal to a upon 2, when it reaches here, let's say time in the watch is t. So at time t, the body reaches at x equal to a by 2. It's clear? So keep it in mind. Now I'm using this equation, x equal to a sine omega t plus alpha. As I told you, the time counting started from the mean position, right? So alpha has to be 0. So put here alpha 0. It will be simply sine of omega t equal to x, right? Now if I put x equal to a upon 2, suppose when body is here, when body is here, whatever x is there and whatever t is there, that x and t I will put in this equation. So x I will put a by 2. If you put x equal to a by 2, this small t that is there, it is a time that is from 0 to t, time taken to go from here to here. This t is there. So cancel it. Sine omega t is equal to 1 upon 2. You know that sine of 30 degrees is 1 upon 2, right? So omega t must be 30 degree. 30 degree in the sense pi by 6. So omega t must be pi by 6. Omega you write down as 2 pi by t into small t. It's pi by 6. This capital T that you can see, it's a period of oscillation, right? Cancel. Small t you can easily get. It's capital T divided by 2 into 6. That is 12. So here we proved it. Okay. So this way you can find out the formulas. Okay. So time taken to go from x equal to 0 to x equal to a by 2. Please remember it is t upon 12. Got this? Okay. So let me come back to this formula. So from here to here, it's t by 12, and then it is a double time, 2 times t by 12, that is t by 6. Similarly, when the body comes back from extreme position to mean position, this time is again 2t by 12, and this time is half of it, that is just t by 12. So same time is there when you come on the back side. Okay, so I hope this concept is very clear, right? Okay, let's move to the next point. Okay, so this is the next point now. The next point which I am going to discuss, that I have simply written over here. You just read this point first. If a particle is performing Shm with a frequency f, f is a frequency of its oscillation, then its kinetic energy and potential energy, these kinetic energies and potential energies of this particle, these also oscillate. Kinetic energy and potential energies are also oscillating with a frequency 2f. That is double frequency. If particle has a frequency f, the kinetic energy and potential energy oscillate with a frequency double, that is 2f. Now, this point is written in front of you. You can read it thoroughly. Now, if you want to understand this point, that how does we can understand this point, look here on this example. See, suppose this is a path of oscillation. X equal to 0, it represents mean position. And x equal to minus a, it is a negative extreme. And x equal to plus a, it is again a positive extreme. Okay. Now look here. To understand this point, I'll give you one simple example. Suppose when the body is here, it's a point A, and this point I'm calling as B. Okay. Now listen carefully. When body is at A point, suppose the journey started from A point. From A, the body will go to B, and from B again it will come back to A. So when the body comes back to A, this is one oscillation, right? So that is one oscillation. Now let's see during this one oscillation how kinetic energy and potential energy are changing. So look here. First of all, I'll begin with kinetic energy. Now look here. When body is at A point, A is the extreme position, isn't it? At extreme position, you know that the body stops at extreme position. So at extreme position, kinetic energy of the body must be 0. When the body reaches to mean position, while going here, the body reaches to mean position. At mean position, its kinetic energy become maximum. Okay, the kinetic energy never goes in negative in this chapter, and even potential energy also never goes in negative in this chapter. Okay, so here x0 kinetic become maximum. Then when it reaches to the B point, the kinetic energy again becomes 0, right? Because B is also extreme place. So see, kinetic energy, if you observe, it is changing from 0 to max and then max to 0. But it is not going in the negative. Okay, so if I just plot here the graph of kinetic energy, okay, versus time if I plot. So kinetic energy is changing from 0 to max and then max to 0. Can you see this one? So kinetic energy changing from 0 to max. This is suppose max. And then again 0. Okay, so this is actually one cycle or one oscillation of kinetic energy. Kinetic energy never goes in negative side. Its kinetic energy cannot be negative. Now, the body has reached to the B place, right? From B, again body will reach to this side. Okay. So when body comes back, the kinetic energy will change from max to 0 again. Oh, sorry. When it comes back, the kinetic energy will change from 0 to max again, like this. And when finally body will reach from here to here, again kinetic energy will change from max to 0 finally. So this is one more cycle. Okay, so if you can see the body starting from A, when it comes back to A, it's a one oscillation. So when the particle completes one oscillation, till that the kinetic energy has already finished its 2 cycles. The kinetic energy has two times it has changed from 0 to max, max to 0, and again from 0 to max and max to 0. So kinetic energy oscillated twice. 2 cycles it has completed, when the body has completed only one oscillation. That's why we can say that frequency of oscillation of kinetic energy is a double of the particle. Okay, the same way as I explained you kinetic energy, same way potential energy can also be explained. In this chapter, potential energy also does not go in the negative side. Potential will also be 0 or maximum. Okay, so that's why this point is very much true. So in the time when particle completes one oscillation, remember kinetic and potential energy, they complete their 2 oscillations. 2 times they vary from 0 to max and max to 0. Okay, so try to understand this. Okay, so this completes your point. Okay, let's move to the next point now. Okay, so now we'll discuss the next point. The body losing contact in vertical SHM. Okay, it's an important point. See to it. Now let's understand this point. Suppose here we are having a one horizontal platform is there. Let's say this is a horizontal platform. Okay. See, this is some horizontal platform. Look at this. And this horizontal platform is performing oscillation or SHM between the top and the bottom point. This way it is oscillating. See, look at this. This way it is suppose continuously oscillating. Okay. So this upper extreme place, this is like a highest point of its oscillation. It's an extreme position actually, and this is the lowest position of its oscillation, right? And this is the mean position. So between these 3 points it is continuously oscillating like this. Okay, now here above this platform, above this horizontal platform, we have kept a one body, or you can say one box. We have kept box of mass m. It's a body of mass m. So since it is kept over the platform, it also oscillates along with the platform, right? This way it is oscillating continuously. It is going up, then coming down, and this way they are oscillating. Now what happens during this oscillation continuously? Its oscillation is going on. During this oscillation, there is a chance that the box may leave the contact with the platform. The box and platform may get separated. The separation usually occurs at highest point. The box and the platform can leave the contact, and this can happen particularly at highest point. So today we have to understand that why they are leaving the contact, under what condition box is leaving the contact with the platform, okay, and how to prevent that. Okay, that we have to see. Now look here. Suppose the body and the platform both are oscillating like this. At a highest point, if I talk, at highest point, the forces acting on this body will be, downward force will be mg, the upward force will be normal reaction, right? This you know. And now look at the highest point. When the platform reaches at highest point, from the highest point the platform start falling down like this with acceleration a. Okay, it's acceleration a because it is performing SHM. So from highest point, at highest point, its acceleration with which it will fall down. You know that acceleration at any point is given by omega square x. Right? Okay, negative sign we can ignore. Okay, magnitude is omega square x. Now this highest point that you can see, highest point is means it's an extreme point. At extreme point, x will be equal to capital A. So this is a acceleration. Okay. So at highest point, the platform is at highest point. At highest point, the platform starts falling down with an acceleration which is equal to this much, omega square A. Right? So if a platform is falling with the acceleration omega square A, so the body on it, it will also fall with the acceleration omega square A. Right? So for this body, you can see the forces acting on the body is mg and n. Na? So for this body, I can write down that mg minus n, it's a net force on the body. Okay. So net force can be written as mass of the body into its acceleration by Newton's second law. So it's mg minus n. Acceleration, as I told you, it is omega square A. The platform will do the oscillation with the acceleration omega square A. So if the body is in contact with the platform, the body will also oscillate with the acceleration omega square A at this point. Okay. So here, from here you can get the value of n. N will be m in the bracket g minus omega square a, right? Okay. It's a value of normal reaction. Okay, it's a normal reaction that it is getting. As long as it is getting the normal reaction, that means the platform and the body are in contact. When the contact is broken, this n becomes 0. You know that. If contact is broken, normal reaction becomes 0. So as long as they are in contact, the normal reaction is given by this formula. Now if you see, here one term is there, g minus omega square a. If we increase the omega, how can you increase the omega? Omega is given by 2 pi into frequency. So if you increase, the omega will increase. So if you increase the omega, or you can increase the x amplitude also, a if you increase. If you increase omega or you increase a, this term will definitely increase. Okay. When this term, omega square a, this term that you can see, if this term become equal to g, when g become equal to omega square a, these two terms become equal. At that time, normal reaction will become 0, isn't it? Okay. So when g become equal to omega square, normal reaction becomes 0. Okay. And if suppose omega square a become more than g, then the normal reaction will come negative, which is not possible. Negative normal reaction does not exist. So this is a condition when the contact will be broken. If n becomes 0, it's a case of contact is broken. So contact will be broken when g become equal to omega square a, or if g become less than omega square a. So contact will be broken, or contact is just broken, you can say, when g become equal to omega square a. Okay. Or if g become less than omega square a, under this condition, okay, the contact will be definitely broken. Okay, the contact will be maintained if g is more than omega square a. Okay, so keep in mind. So this formula you need to keep it in your mind. From this formula, sometime omega will be asked to you, or sometime frequency you have to find out. Omega can be written as 2 pi into frequency, or sometime frequency will be given and a you need to find out. Either a they will ask you, or omega they will ask you. Okay, so this is a condition at which the contact will be lost. Okay. So for contact to be lost, if they ask you amplitude, at what amplitude the contact will be lost, how much should be amplitude so that contact is lost. So when amplitude become greater than or equal to g upon omega square, at this point the contact will be lost, right? So the maximum amplitude that we can keep without losing contact, the maximum amplitude will be g by omega square, that we can understand. Okay. So this way, sometime amplitude they will ask you, sometime omega, sometime frequency. So you have to do it accordingly. So remember, this is a condition under which the contact will be broken. Okay. See, getting? Okay. Like this, it is oscillating. Okay. Physically, if you want to understand this thing, I'll explain. Suppose this platform is oscillating continuously. At highest point, the acceleration of the platform is downward, and it is maximum acceleration. That is omega square a. So since acceleration is downward and it is maximum also, at this point the normal reaction is minimum. Normal reaction is minimum at this point. Okay. If normal reaction becomes 0, it's a loss of contact. And when the normal reaction becomes 0, if this omega square a become more than g, if omega square a become more than g, the contact will be lost. Okay. So keep it in your mind. Okay. So this completes your oscillation point. Now we'll move to the next point. Okay, so the next point is now the combination of springs. In the oscillation, there are some questions in which a spring is also involved. You know that if you connect a spring with a block, the spring and block together can perform oscillation, right? Now see, let's start this topic, combination of spring. Now suppose when you take a one spring like this and connect it with a block like this. Okay. Now if you shift this block from its initial position, suppose here if you shift it by x meter, the spring will stretch by x meter, right? When the spring will stretch by x meter, the spring will produce a restoring force F. F is the restoring force produced by the spring. This restoring force, you know, that's given by minus of kx, right? This K, which is actually a force constant, this K depends on the spring. It depends on the elastic properties, the shape of the spring and all other factors. Okay, the K here, it's called as a spring constant, but it is also known as stiffness. The another name for the K is stiffness. K is different for different springs. Okay, the spring which produces a more restoring force for the unit displacement, that spring will have a higher value of K. K is different for different springs. Okay, now today we will see the combination of springs, that is the springs in series and parallel combination. That look at this diagram. If you look at this diagram here, anybody can see that there are two springs and they are in parallel, right? The springs are here in parallel. Okay, you can check that. Okay, springs are here in parallel. Now in parallel, what is the important condition that to be followed? See, if suppose this block goes down by x meters, okay, then you can understand the both springs will stretch by by x meter, right? So x will be same in both the springs. The elongation, the stretching will be same in both the springs. So whenever x is same in the two springs, then they are said to be in parallel. For parallel, x has to be same. Okay. Now, if you look at this diagram, here also these two springs, you may be feeling that these springs are in series, but no, these springs are also considered to be in parallel. Why? Because if this block goes down by x centimeters, you can understand the upper spring will stretch by x centimeter and the lower spring will compress by x centimeter. Stretching and compressing, it's no problem, it can happen, but both of them, upper and lower spring, will be deformed by x centimeters. Na? So x will be same in both the spring. No doubt, one will be compressed, other will be stretched. But x will be same for both the springs. So that's why these two springs are also considered to be in parallel. So this can be there. Now in the parallel, if you want to find out the equivalent spring constant, the K equivalent if you want to find. Okay. Equivalent K. In the parallel combination, equivalent K is given by this formula, K1 plus K2. The equivalent K is given by this formula, K1 plus K2. Now obviously, you may be confused that how this formula came. Okay. So for that I will give you proof of this formula. But it is a formula by which you can find out the equivalent K. Okay. So let's see the proof of this formula. Okay. See, for proving this formula, I am taking a case of parallel springs. Okay. It's K1 spring constant and the another spring constant is K2. This is a case of parallel springs, right? Now as I told you, suppose this block goes down by x meters. Okay. So both the springs will stretch by same x. Here x will be same. Okay. So in the first spring, the restoring force that will be produced, it will be K1x, right? In the second spring also the restoring force which will be produced, it's K2x, right? So you can see the total restoring force that they are producing. How much it is? It's minus K1x and minus K2x. Negative sign just indicate that this force is opposite to the x displacement. Displacement is downward, the force is upward. That is the meaning of minus sign. If you take a minus common, it's K1 plus K2 into x. Right? This is the total force produced by this combination, right? Clear? So if you replace this system of two springs, there are two springs are there. If you replace the system by a single spring, the single spring will produce same effect as produced by these two springs. Okay, so the equivalent K, the K of this spring will be known as K equivalent, right? So this is an equivalent spring. That is, this spring will perform same function as done by these two springs together. Okay. So for this spring, it will do the same work. So here the block goes down by x meter, right? Here also same block will go down by same x. Okay. So for this block, I can say the restoring force will be minus K equivalent into x. Okay. So if you just compare these two, this is a force is produced by the two springs together, and this is a force produced by the equivalent spring. If you compare these forces has to be same. If on comparison you can get that K equivalent must be K1 plus K2, right? So this way we can prove it. So this is called springs in parallel combination. I hope it's clear to you. Then I will go with a combination springs in series. Springs in series we will discuss. Okay. Now let's see how to discuss spring in series. Okay. See here. If suppose two springs are this way, this is one spring and then another spring is this one. And below them block is connected. Okay. These both springs are light. In this topic we always assume that springs are light. That means spring do not have mass. Springs are light. Okay. Now tell me one thing. As soon as you connect it, it will be pulled down by the gravitational force mg. Okay. Because of that it will go down. This block will go down. Both the springs will stretch. If the first spring stretches by x1, the second spring stretches by x2. So you can understand the block will go down by the x1 plus x2, right? The displacement of the block will be x1 plus x2. Here, after going down, suppose the block stops. The block comes in equilibrium. So when block stops, the upward force on the block must be equal to downward force, right? The upward force will be restoring force. The restoring force will be produced by first spring and also it is produced by second spring. This is all going to happen. Now in series what happens? The force which is produced by first spring. Can you see? The restoring force which is produced by first spring. That force will be equal to mg. The restoring force produced by second spring will also be mg. Okay. Here both the springs produce the same restoring force. Okay. Here x is not same for both springs. The elongation is not same for both springs. Here f is same for both springs. Here students often get confused at how this happens. See, you imagine the first spring. Just look at the first spring. The downward force that first spring is experiencing, downward force is mg. So upward force also it will produce mg. Okay, to balance. Similarly, if you look at the second spring, the downward force on the second spring is also mg. So upward force that it produces to balance, it's also mg. Okay. Both the spring, remember in the series combination, the restoring force produced by both the spring is same. So whenever the two springs produce the same restoring force, then only they can said to be in the series combination. Okay. Now here force has to be same. Remember. Now here we can prove it that the K equivalent is given by 1 by K1 plus 1 by K2. Like this. Okay. So earlier for parallel combination I proved the formula for K equivalent. This time I am not proving. The main idea I have given you. The main idea is when the two springs produces the same restoring force, okay, then only they are said to be in the series combination. In series force must be same, restoring force. Okay, so this K equivalent I am not proving. This is I am leaving as an exercise for you. You try to prove this formula. Okay, if you are not getting the proof, you can ask in the doubts that this you are not getting. You can ask as a doubt. Okay, so this is called springs in series and parallel combination, right? Now related to springs, we'll go further. Okay. See, first of all, you should know that if this is a spring and block oscillator like this, every spring has a fixed value of K. The time period of this oscillation, if anybody asks you, time period of this oscillation will be 2 pi root of m by K. Right? And the frequency of this oscillation, frequency will be reciprocal of time. It's 1 upon 2 pi root of K by m. Right? Now, apart from these formulas, there are few more formulas which we need to understand. Okay, so related to springs, I will tell you next formula, that is cutting of spring. Okay, let's see what happens when you cut the spring into 2 parts or 3 parts. See, imagine that we are having this spring. It's the original spring. Its constant is K. K is a spring constant, and the length of this spring is L. Okay. Now, what happens? It is a simple rule that K of any spring, K of a spring is inversely proportional to the length of this spring. That means if you by chance, if you decrease the length of a spring, that means if you cut the spring into 2 parts, the length of each part will decrease. Now, if you decrease the length by cutting the spring, if the length is decreased, K gets increased. Okay. Now, some students may be having a doubt in this formula also, that how this formula came. Okay. So this formula I will prove after a few minutes. I will prove this formula. But as of now, we will remember it and go ahead. That K of the spring is inversely proportional to length of spring. Okay. Now listen, if you cut this spring into 2 parts, let's say we cut this spring into 2 parts. See this. Both the parts need not to be of same length. They may be different length. Suppose one is longer path, L1, and another part is shorter one, L2. Okay. See to it. So spring constant will also change. Its constant will be K1 and K2. Okay. Now, since you know that K is inversely proportional to length of a spring, so on removing this proportionality, we have to put constant. So we can understand KL product is constant. Okay. KL product is constant. So here what you can do this way. For original spring, you take KL product. It's equal to, since KL product is constant now always, for particular spring, KL product is always constant. So when you cut the spring into 2 parts, the material of the spring is same only. The 2 parts are made up of same material as of original spring. So for all these 3, original and the 2 parts, for all these 3 springs, we can apply this formula that KL is constant. Okay. So K into L for the original spring is equal to K1 into L1. It's also equal to K2 into L2. All these 3's are constant. So we can take this equal. Now, over here, sometime when you do the numericals on this topic, sometime you have to take first 2 terms equal, sometime you have to take second and third term equal, sometime first and third term equal, like that. So this way, by using this formula, here if you can see, total 6 quantities are there, 6 terms are there. Out of these 6 quantities, any one you have to find out. Okay, so this is a formula for cutting of a spring. If spring is cut, remember, length decreases, K increases. K is inversely proportional to length. Okay. Now, in this formula, some student must be having a doubt that how can we prove that K is inversely proportional to length of spring? So that I will try to prove it for you. But for proving this point, you should have a knowledge of elasticity. That is Young's modulus and all, stress and strain, that point. Okay. See, let's see the proof of this formula. Okay. See, imagine that it is a metal wire or it is an elastic wire. First of all, I am taking. Here I am taking spring. Okay. The spring is also made up of elastic material always. Spring cannot be a non-elastic material. Spring is also elastic. Now you can see these 2 diagrams. You may feel that these 2 are the different objects. Yes, these 2 are different things. But the working of these both is same. See, whenever you pull the elastic wire, in the elastic wire, restoring forces are produced, right? Okay. Similarly, when you pull the spring, in the spring also restoring forces are produced. In case of elastic wire, these restoring forces which are produced divided by area, this is called stress. F by A is the stress. Okay. And since you are pulling this wire, in the wire elongation is also produced. Let's say elongation is X. X is the elongation. So x upon L if I do. Okay. If you look at it, this is stress upon strain. It is equal to Young's modulus, right? So Young's modulus is given by this formula, FL divided by XA, right? This you know, I think, right? So here if you calculate the formula for F is a restoring force also. F will be YAX by L, right? Here in the elastic wire also, up to elastic limit, F is directly proportional to X, we can say. In the wire also, F is directly proportional to X up to elastic limit. You might be knowing this. So this relation is there. So here YA by L is a constant. F is directly proportional to X for elastic wire. And for spring also you know that F is directly proportional to X for spring. In case of spring, F is equal to Kx we can write. So these two formulas if you compare, okay, one formula is for the spring and the second formula is for elastic wire. If you compare, you can understand that K of the spring is similar to YA by L. Yes, this happens. See, when you take spring like this, the K of this spring, it is equal to YAL of the wire. Like that. Okay. You can understand that this is a formula for K in short. Y is a Young's modulus of this wire, A is a cross-section area of the wire of the spring, and L is the length of this spring. So you can see clearly here K is inversely proportional to length. Right. This way you can understand. Remember, the wire and the spring, you may feel they are different, but they are actually same things. So the formula that I derived for wire, that can be applied for the spring as well. Okay. So K of the spring is inversely proportional to length of the spring. So I hope this formula is clear to you. Okay. Let's move to the next point. Okay, so let's discuss a new point now. Next new point is angular SHM. Okay. Angular SHM is also a type of SHM in which rotation is also involved. It's a SHM along with rotation. Now what is angular SHM? See to it. Suppose we are having a particular body like this. Look here. Any body we are having, let's say this we are having a body, and right now this body is in equilibrium. It is at rest. It is resting. It is in equilibrium. Okay. That is, no torque is there, no force is there on this body. Okay. Now, if we displace this body from its equilibrium position slightly, let's say we displace it like this. So the displacement of this body, the angular displacement, if I talk, the angular displacement is theta. Okay. You can see that. Now suppose the situation is like this, that whenever you displace it by theta angle, now on this body a torque starts acting. Torque, or you can say first of all force will act. The force will produce a torque. Torque will start acting on the body. Suppose this situation is there. I'll give you practical example of this point, but first of all let's understand this. So suppose as soon as you shift this body from equilibrium position, torque starts acting on this. This torque is trying to restore the body in the equilibrium position. That means this torque tries to bring the body in the equilibrium position. It's basically a restoring torque. It is trying to bring the body back to the equilibrium position. So what happened? This torque is supposed directly proportional to theta. Torque is directly proportional to theta. But it is opposite to the theta. That means as the theta is in anti-clockwise direction, theta you are covering in anti-clockwise direction, this torque wants to rotate the body in the clockwise direction to bring it in equilibrium. This torque is against the theta, it's opposing the theta, but torque is proportional to theta also. Suppose this condition is there. If this condition is followed, if this condition happens, then we can say this body starts performing SHM. How? See what happens, because of this torque, the body starts rotating in the opposite direction, in the clockwise direction, like this. Okay, and because of this torque, the body will come back to the equilibrium position. But when the body comes to the equilibrium position, the body will gain some speed. Torque is acting now. Because of the torque, the body will accelerate. Torque will produce angular acceleration. The body will not stop in equilibrium position. Body will go like this, and the body keeps doing this way. See, look at it. This way body will do. So this is called Shm. It's actually oscillating between two extreme places. One extreme place will be above equilibrium and one extreme place will be below equilibrium. Start oscillating this way, like that. Okay. So this kind of oscillation in which actually the body will rotate this way. Look at it. This is actually rotation also, and it is oscillation between two extreme places. Okay. So this type of oscillation is known as angular Shm. Okay. So in angular Shm, the very important condition is torque is proportional to theta. This formula, torque proportional to theta, it is similar to this formula. Right? These two formulas are similar. The role of force is being played by torque, and the role of x is a linear displacement. It's played by theta. Theta is the angular displacement. So these formulas are similar. When the body follow this formula, F equal to kx, this formula when it follow, it is said to be a linear Shm, right? Which we have studied till now. And this formula, when the body follows, it's called as angular Shm. Okay, so keep it in mind. Now, in the angular Shm, as I told you, torque is proportional to theta. In the next step, when we remove this proportionality sign, we have to put constant, right? Constant is C. C is a constant. C is known as a torque constant or twist constant sometimes. C is a torque constant, or it is also known as torsional constant. C depends on the conditions which are providing the torque. C depends on those things which are providing the torque. If suppose torque is provided by a magnetic field, let's take example, torque is provided by a magnetic field. So C will depend on that magnetic field. Okay. C depends on the conditions which are providing the torque. Okay. C can be different in different situations. This is there. Okay. So keep it in mind, this formula. Then torque can be written as I into alpha. Yes. Torque acting on a body can be written as I alpha minus c theta. So alpha, that is angular acceleration of this body. Alpha is the acceleration of this body at any moment. At any moment, torque acting on the body can be written as I into alpha of that body. Right? Alpha is minus c by I. It's into theta. C by I is a whole constant. Okay. Alpha is equal to minus c by I theta. Just keep it in mind. Okay. Now, if I go with a linear Shm, in linear Shm, you know that F is proportional to X. F equal to minus Kx, we can write. These two formulas are similar to each other. Now here, torque you written as I alpha, right? Similarly, in the linear Shm, F can be written as Ma. Equal to minus. So pass M on that side, acceleration can be given by minus K by Mx, right? So look at this. This formula of linear acceleration, and this is a formula for angular acceleration. Both are comparable, you can see. A is in the place of alpha, and K upon M is in the place of C upon I. The role of M, see this M is a mass. The role of mass is here played by I, that is moment of inertia. And the role of K is played by C. Okay. Now, you might be knowing that acceleration in the Shm is given by minus omega square x, right? So, this K by M is written as omega square, na? K by M is replaced by omega square. Similarly, here also, C by I can be written as omega square. Yes. You can say minus C by, okay. You can say the omega square is C upon I. Yes. So, in angular Shm, the omega square is given by C upon I. Okay. Okay. Keep these formulas in your mind. Okay. Now I'll give you one practical example of angular Shm, the proper example of linear angular Shm. Okay. See to it. The practical example of body which performs angular Shm, example is compound pendulum. This topic, compound pendulum, is useful for JEE exam particularly, but other students also can see. Okay. The compound pendulum, it is also sometimes known as physical pendulum. Okay, let's see what is compound pendulum. Okay. Imagine that if I take one rod like this, okay, it's a one rod of length, let's say L. Okay. the one end of the rod, the upper end of the rod is A, and it is fixed in a roof. Okay, it is fixed rigidly in the roof. Okay, the center of mass of this rod, center of mass is C, and the other end is B. Okay, so it's a rod AB, and C is the center of mass. Okay, now initially this rod will be in this position. See this. Initially, suppose the rod is in this vertical position. When the rod is in vertical position, the rod will be at rest. The rod will be in equilibrium. Okay. From its equilibrium position, suppose we shift the rod on this side. This way we shift it. Okay. Such that this angle formed is theta. So you can understand that theta is the angular displacement. Now here if you look at it, mg force will act this way. Na? This way mg force will act. Now look at this. This distance, obviously it will be L by 2. I know that it will be L by 2. Okay. But this distance I am naming as D, suppose. I am writing this distance from A to C as a D. You can say that D is equal to L by 2 also. It may or sometime may not be equal to L by 2 also. Okay. If the rod is non-uniform, made up of non-uniform material, then center of mass may be somewhere other than middle point. Okay. So this I am writing as D. Now look at it carefully. Now you know that if you leave the rod in this position, in this tilted position, if you leave the rod, you know that what will happen to the rod. Rod will do like this. Okay. Now you may feel that it is like a pendulum. Okay. But if you look at it, rod is rotating actually. Okay. Rod is oscillating plus rod is rotating also. So actually rod is performing angular Shm. Okay. So now today we want to find out, suppose, the time period of this angular Shm. We have to find the time period. So see how to do it. Here I can consider that A is a fixed point, or axis of rotation is passing through A. The axis of rotation is passing through A. Then here is a C point. This distance is D. This is the way mg force is acting, right? Mg force can be shown from the C point, na? And look at it. This angle is theta, right? So this is a simplified diagram of this. Now if you apply simple trigonometry, you can understand this side. Can you see? This side will be d sine theta. Okay. So if you look at it, d sine theta is a perpendicular distance. D sine theta is a perpendicular distance of mg from the fixed point. The perpendicular distance of mg from the fixed point is d sine theta. So because of this mg, torque will be produced. Torque is acting on the rod. Torque will be this one, mg into d sine theta. Okay. It's a torque produced by the mg. Okay. Now if we assume here theta angle is small, let's assume that it is a smaller oscillation. The rod is oscillating with a small theta. Theta is not big. If assume theta is small, we can say sine theta is nearly equal to theta in the radians. This point you might be knowing. For smaller angle, we can write this one, that sine theta is nearly theta. Okay. So ultimately this formula will become torque equal to mg d theta. Okay. Here we can say mgd is constant. Na? Whether rod is in any position, the mg of the rod and the d is constant. The mgd is constant. This constant I am writing as a c. So you can get the formula torque equal to c theta. Okay. Negative sign you won't get here. Negative sign actually indicate that torque is just opposing the theta. That you cannot get here, because here we are writing just a magnitude of this torque. Okay. If you write down the torque in the vector form, then negative sign can come. Here we are just writing magnitude of the torque, this one. So only magnitude will come. So torque equal to c theta. By looking at this equation, we can understand that it is an angular Shm. Okay. Okay. Now here, as you remember, it is a case of angular Shm. Here, torque acting on the rod can be written as I alpha c theta. Alpha will be c by I into theta. If you compare this formula with this one, A equal to omega square x, we can understand that omega square, in case of angular Shm, omega square is c by I. So omega will be root of c by I. Omega you can write down as 2 pi by time period. Okay. From here you can get time period. The time period will be given by 2 pi root of I by C, right? 2 pi root of I by C. But if you remember, C is actually mgd, na? In case of compound pendulum, C is mgd. So time period will be given by 2 pi under root of I upon C. So C you write down as mgd. So ultimately you will get this formula. It's a formula for time period of physical pendulum, or you can say compound pendulum. Okay. So compound pendulum is a name for this structure, and it oscillates like this. So it is called compound pendulum. Okay. Okay. Here don't think that bob is connected in the bottom and all. No, it's not at all any bob is there. It's not a string and bob. It's a simply rod which is oscillating. Okay. So this thing is known as compound pendulum. Okay. And this is the time period of compound pendulum. 2 pi under root of I upon mgd. I hope it's clear to you. Okay. Let's move to the next point. Okay, students. So let's go for the next point in the oscillation. Some examples of oscillating system. In this one, I will tell you some different examples of those bodies or those systems which can perform oscillation. Okay, and in this one we will also find out the time period of those oscillating systems. Okay, see the first example. First is a tunnel dug into earth. It's the first example, tunnel dug into earth. See to it. Suppose this is our earth, okay, and this is center of our earth. Here if you make a tunnel like this way if you make a tunnel, across the diameter of the tunnel, across the diameter of the earth, if you make a tunnel like this, okay, in this tunnel if you release any stone, suppose here we are having some stone or some body we are having, if you release the body from earth's surface into this tunnel, definitely the body will go like this. It will go down because of the gravitational force. When the body reaches to the center of earth, gravitational force become zero on this body. Okay, because it already reaches to the earth center. Okay. Then the body will go down like this, because when it passes through the center, this body will have a speed. So it will not stop at the center, it will go down, and as it goes down, the earth will pull it backwards like this. Earth will pull it again like this. Okay. And when it is up, earth pulls this way. So earth always pulls this body towards the center of the earth. So in this case what happens, this particle starts performing Shm. It performs oscillation. Okay. First of all, we have to find out the time period of this oscillation, suppose. Okay. This way the body performs oscillation. Huh? Okay. Now look here. If suppose, first of all, if you want to prove exactly that how, suppose we have to exactly prove it that how it is Shm. So for that I am telling you, suppose when the body is here, this distance is d, okay, and this distance is, it's a distance from center, it is, let's say, x I am taking. Okay. When the body is here, let's say distance is d, and from the center its distance is x. You can understand that x plus d is equal to radius of earth, right? This point we are having. Now when it is at depth d, body is at a depth d, the gravitational force acting on this and the acceleration due to gravity at the depth is given by this formula, g 1 minus d by r, that you know already, right? Now multiply both sides by small m. Small m is the mass of this body. Okay. And here I am just solving it a little bit. It is this one, right? Now what is r minus d? As you can see, r minus d is equal to x. Okay, it's x mg divided by r is equal to this mg. This, can you see? It's a force which is acting on this particle at the depth d. So this mg is the restoring force which is pulling it towards center. You can see that this force which is acting on the body, it is directly proportional to x. Mg upon r is a constant, na? Okay. Okay. So this is a clear case of oscillation. It's a linear Shm. So this way we can prove that it is a Shm. Now we want to find out the time period of this Shm, right? So if you compare this formula f equal to kx, okay, if you compare the formula f equal to kx with this one, so you can understand that k is equal to mg divided by r. Yes, k is equal to mg divided by r, that I am writing here. The k, that is force constant, is equal to mg divided by r. Now k upon m will be g by r, right? K upon m is written as omega square. in the oscillation. So omega will be root of G by R. Write down omega as a 2 pi upon time period. Using that T you can find T will come 2 pi root of R by G. This is a formula for time period of the oscillation of this body inside the tunnel. Okay. See this whole argument carefully. Okay, I hope you will understand this. Okay. So remember, whenever you are having a tunnel like this into the earth, this way, it's a tunnel. Okay. In this tunnel, whenever you leave any stone or any body, it performs Shm of this time period. Okay. Now here, if I put the radius of earth as a 6,400 kilometer, and if I put small g as a 9.8 meter per second square, if I put, on solving this, definitely T I will get, right? T will come 84.6 minutes. This time period will come 84.6 minutes. Okay. So within this time, it is less than 1.5 hours. It's even less than 1.5 hours. Within this time, this body will complete its one oscillation. That is, it will start from the top, goes to down, and again it will come to the top. Okay. Now here, one doubt can come that here the tunnel that we have made, it is diametrically. It's passing through a diameter. If we make some other tunnel this way tunnel, it is along the chord of the circle, right? It's a tunnel which passes through the chord of the circle. Okay. Or if we make a tunnel this way, and in this tunnel, if we release the stone, what happens? So directly I am telling you, if you make any tunnel along the chord, if you make this tunnel, in this tunnel also the particle will perform Shm only, and the time period of this Shm will be given by same formula, this one. The formula remains same. Same formula you can apply for any tunnel actually made into the earth. For any tunnel made into the earth, if you leave it like this, the time period is given by this formula. Now this point I am not proving. Take it as an exercise. You try to prove this point. If still you are not getting this point, that how it is same time period for any tunnel, then you can ask me as a doubt. I will explain it to you. Okay. So remember, and the value of 2 pi root of R by G is equal to 84.6 minutes. Okay. So I hope this first example is very clear. Okay. Now I am going to the second example of oscillating systems. See. Suppose this is YouTube. You know the YouTube, right? The YouTube which is made up of glass. It's a YouTube made up of glass. Okay. In this YouTube, suppose we fill up some liquid, mercury or maybe any liquid, like this. So initially the level of the mercury or level of the liquid will be same in both the arms, na? Like this, right? So this level is H meter. Mercury is filled in up to the height of H meter in the both arms. Okay. The horizontal portion of this YouTube, the horizontal portion is negligible. It's almost 2 vertical portions only. Okay. Now, if you press the mercury from one side if you compress it by, let's say, X meters, so definitely on the other side it will rise by X meter, isn't it? One side you compress it by X meter, other side it will rise by X meter, and then you leave it. Okay, so see, one side is down and another side is up by X meter. As soon as you leave it, the mercury in the both arms will start performing oscillation. It will perform oscillation. Its time period can be given by 2 pi under root of H by G. Okay. It's a shortcut formula that you can remember. Again, I suggest you try to find its proof, that where you can ask your teachers, some other teachers if you are having. You ask them. If then also you are not getting, you can ask me. I will give you the solution. Don't worry. This is a formula for time period of this Shm. Getting the method of proving this time period will be very similar. You try to find out the restoring force which act on the mercury. Okay, and try to prove that a restoring force is equal to Kx. Okay. From that you can find out the K divided by M. You do K upon M. M is a mass of this oscillating liquid. K upon M will give you omega square. Using omega you find out the time period. That can be done. So this I am leaving as an exercise to you. You try to prove it. Third example I am giving. See, suppose if it is a container which contains some liquid. the density of this liquid is sigma, suppose, sigma. Okay, in this liquid we are having a cylinder which is partially inside and partially outside. This, see, like this. See, somewhere it is inside and some part is outside. This happens, the cylinder is floating, right? This happens when the density of this cylinder is less than liquid, right? This only happens when density of cylinder is less than liquid. Suppose density of the cylinder is rho, so rho must be lesser than sigma. Okay. Now this cylinder is floating, it is at rest. Now if you compress this cylinder, I can't say compress, if you displace this cylinder downwards, if you slightly depress this cylinder downwards, suppose this cylinder slightly goes downward by x meters and then you release it. On releasing this, cylinder will also start performing oscillation under ideal conditions. Okay, ideally you have to depress this cylinder vertically downwards and then leave it. It will start performing oscillation. The time period of oscillation of the cylinder is also given by one similar formula, 2 pi root of h by g, almost similar to this. Here h is the height of the cylinder. H is the height of the cylinder. It's after h by g, you have to write down here rho and here also sigma. Slight difference is there. 2 pi under root of h by g into rho upon sigma. Okay. See, as I told you, all the formulas can be proven. You can get the proof of this formula somewhere. Okay. You try to find their proof. If not getting, you can ask me as a doubt. I will explain these points. Okay. So this is a time period of oscillation of this cylinder. Okay. Getting? So we are discussing different oscillating systems, right? In this different oscillating systems, I'll take one more oscillating system. If it is a magnetic field over here, it's a magnetic field B. In this magnetic field, if I leave a magnetic dipole, let's say it is south pole and this is north pole. Okay. So from south to north, this one, it's a direction of movement, dipole moment, m bar. The angle between m bar and b bar is this theta. So you have seen this case in the magnetism chapter also. When you leave this bar magnet into this magnetic field, the magnetic field will exert torque on this dipole. The torque acting on this dipole is given by mb sine theta. Do you know that? Torque acting on this is given by mb sine theta. Okay. Now if I assume that the theta is small, let's consider that theta is small. So sine theta can be nearly theta in the radians. Okay. mb. This can be written. This can be written when theta is assumed to be small. Again here m and b are constant. M is a dipole moment. B is a magnetic field. They are constant. Torque is directly proportional to theta. As we increase the theta, this torque will also increase. As I told you, it's a clear case of angular SHM, right? When this condition is there, it means it's an angular SHM. Okay. When you remove this proportionality sign, constant is C. Remember, we have discussed it earlier. So C is in the place of MB, na? Or you can say MB is in the place of C, you can say. Okay. Now, C we got. When you do C divided by moment of inertia of magnet, C divided by I. I is a moment of inertia of magnet. Okay. And then you take a square root also. This is nothing but formula for omega. Remember, we had discussed it earlier. Omega is root of C by I. Okay. So you can say omega is root of MB upon I. It's a case of angular SHM. Please remember. The magnet will perform angular SHM. The omega can be written as 2 pi by T, root of MB by I. On solving it, you can get time period from this. Time period will be 2 pi under root of I upon MB. It's a formula for time period of a magnet which is oscillating inside the magnetic field. Okay, this is a formula. Okay, so I hope this example is clear. One more last example I'll give you, example of oscillating system. Let's see the next example. Okay, so one more example of oscillating system. If you are having a piston which is fitted on the container filled with a gas, see this example. This is known as piston, right? This piston can also oscillate when you compress this piston slightly downward and release it. It can also perform oscillation because the gas is usually elastic. All the gases have some elasticity. So due to elastic nature of the gas, when the piston is compressed downward and release it, it can perform oscillation. So today we want to find out the time period of this oscillating system also. Okay, see how to do it. Suppose the area of this piston, the cross-section area of this piston is A. Okay, the pressure of the gas inside the container, it is P, and the volume is V. Okay, now what happens? Suppose if you press this piston downwards, the piston will go slightly downward like this. Suppose piston is going downward by X meters. It goes down by X meter. In this case, the decrease in volume, dV denotes decrease in volume. Decrease in volume will be A into X, isn't it? The volume of the gas will decrease by A into X. Okay. So obviously the volume of the gas will decrease. So pressure of the gas will increase. Volume and pressure will change. This change, the pressure and volume are changing. Now this change may be adiabatic or it may be isothermal change, isn't it? Okay. Let's consider that it is an adiabatic change first of all. Let's consider that it is an adiabatic change. Okay. In case of adiabatic process on the gas, we can write down that PV raised to gamma product is constant. Remember, you can understand this. Now here you take derivative of this formula with respect to volume or with respect to pressure you can take. Let's take derivative of this formula with respect to volume. So it will be dP divided by dV, V raised to gamma, plus P gamma V raised to gamma minus 1. This you will get when you take a derivative with respect to volume. Okay. Even if you take derivative with respect to pressure, it is okay. You can do. Derivative of constant will be 0, right? So this you are getting. Just solve it little bit. You can solve it little bit, right? On solving it little bit, you will get from here that dP upon P is equal to minus gamma times dV upon V. Okay, you can get it by just solving it little bit. Okay, you can get this formula. Now from here I will get a value of dP. dP will be minus gamma by V into P into dV. Okay, this dV that I have written over here, dV can be written as A times X. Remember, change in volume. This is a pressure. Okay, now both sides if you multiply by area of the piston, dP into A minus gamma PV A square X. And now just look at this system, dP into A. dP is an increase in pressure. The pressure that increases from inside, that increases dP. If you multiply dP with the area of the piston, it will be equal to restoring force which is acting from inside. The restoring force which is acting from the inside on the piston, the restoring force will be dP into A, the increase in the pressure into area. Okay. So dP into A is actually kind of a restoring force acting on the piston by the gas. So you can see restoring force is given by this formula. Here gamma is constant. This P denotes initial pressure and V denotes initial volume. A square is the area of the piston. You can see that F is minus gamma P A square by V into X, isn't it? So these all things, can you see? These are constant. Write it as a K, F equal to Kx you will get from this. So it clearly shows that the piston on which this force is acting, and X is the displacement of the piston, it clearly shows that piston performs oscillation. Okay. Now if you can see, the K, force constant, is equal to gamma P A square by V, isn't it? Here I am doing K, which is force constant, it is gamma P A square by V. Okay. Now both sides if you multiply with if you divide with the mass of the piston, let's say this M is a mass of the piston. Okay. So K by M will give you omega square. So you can get omega from this. So omega will be root of gamma P A square by MV. On solving it, you will get a time period. Time period will come 2 pi under root of MV divided by gamma P A square. This is the time period of the oscillation of the piston if the process is adiabatic. Remember, we discussed adiabatic. If the process is isothermal, the gas is compressed, suppose isothermally. In case of isothermal process, just remember one thing, this gamma will disappear. Rest of the things will be same. In case of isothermal process, it will be 2 pi root of mv divided by Pa square. Okay. Only gamma will disappear if it is a isothermal process. Getting? This is the time period of oscillation of this piston. Okay. So I hope this point is very clear to you. Okay. So here we completed the different examples of oscillation. Still, if you have any doubt in the oscillation, you can ask. But this much is sufficient for NEET point of view at least. So this is all about oscillation. Okay. We'll meet in the next lecture.